Okay, guys, I'm happy to welcome Yannik on the stage. He's going to be our next speaker, and the next talk is going to be on Decentralized Confidential Computing. Yannik is the CEO and co-founder of TUM, and I'm really looking forward to the talk. So a big round of applause for Yannik, please.
All right, thank you very much. Hi everyone, I'm Yannik, co-founder and CEO at TUM, and today I want to discuss decentralized confidential computing, the end of trust. So first, let's begin with what is decentralized confidential computing. Decentralized confidential computing, or DCC, is a transformative shift both for traditional and distributed computing. And why is that? Well, because decentralized confidential computing allows for the processing of encrypted data without having to decrypt that data first. And so what's possible with decentralized confidential computing is to build execution environments without requiring any single trusted entity. To build execution environments that allow for confidential operations, for secure operations over sensitive data, without having to decrypt the data first. And the proprietary internet infrastructure usually requires data to be decrypted and then processed. With the new decentralized confidential computing technology, that changes. So how we arrived at this point is an evolution, and this evolution is a shift from trusted systems to trustless systems in the entire area of confidential computing. And it originally started with trusted execution. And trusted execution relies on trusted execution environments, which are dedicated hardware platforms provided by trusted hardware manufacturers. And they are the product of proprietary trusted supply chains. And there's a manifold of issues associated with these systems. And one of those issues is a high cost for both the hardware itself, but also the maintenance of those systems. Significant performance overheads when switching between insecure and secure contexts, but most importantly, a fundamentally flawed trust model. And the trust model of these technologies is fundamentally flawed because it requires the trust in this proprietary supply chain, which at the end of the day is a chain of single points of failure. And we've seen that happen many times over the last few years. We've seen a lot of exploits, vulnerabilities, and attacks of these hardware platforms, both on the hardware fuse level, but also on the firmware level and the distribution level. And so the way we like to think about trusted execution environments really is as this legacy technology. This technology that can be beneficial, but is not the answer to building confidential computing, especially when deploying systems in a permissionless, decentralized way, because hardware access to those platforms, although the manufacturers try their best, is crucial and allows for these kinds of exploits in many cases. And so the evolution, or here you can see a diagram of how confidential computing would work with trusted hardware, and you can really see that it's essentially just sending sensitive data to some processing unit that runs a TEE, which requires this trust in whoever operates the TEE to not be able to access anything, and also requires the trust that whoever produced the TEE, whoever shipped it, whoever built the firmware has not installed backdoors. And so that's not really ideal. Moving from trusted execution environments hence to cryptographic protocols. And the first family of cryptographic protocols that comes to mind would be zero-knowledge proofs. And zero-knowledge proofs are already heavily being used in the distributed computing space. They essentially allow for the verification of information and execution without having to disclose the sensitive information. So what that means is that in a two-party setting, a prover who has access to sensitive information is able to run some computation with this information without having to share the information and produce a proof that gets transferred to a verifier, and the verifier can be convinced of the correct execution without requiring access to the sensitive data, which is an incredibly powerful concept for privacy and scalability. However, it's not suitable for the kinds of systems that we want to build. We want confidential computing. We want the ability to just send data somewhere and have it be processed without requiring trust, without requiring some party that has actual access to the data. And so this technology is unfit for the end that we are trying to achieve. And the next technology that could make sense is fully homomorphic encryption, FHE. And FHE allows for computations over encrypted data without having to decrypt it, which, as I mentioned in the beginning, is essentially what we are trying to achieve. The issue with FHE really lies in its practicality, which is incredibly limited due to extreme slowdowns, latency penalties one faces when trying to run simple or more complex operations. It's not uncommon to see many orders of magnitudes of slowdowns, right? So 10,000 times slowdowns, which isn't just a latency issue, but also a cost issue, because that proportionally increases the cost. And that's essentially due to costly bootstrapping operations that need to be performed when running specific kinds of operations in FHE. Additionally, FHE also lacks the ability for selective disclosure. Selective disclosure means that information about this encrypted data in many cases should be revealed at some point. When we think about building confidential on-chain applications, there's points in time where information about previously encrypted state should be revealed, and that's not something that FHE on its own can offer. Same with verifiability. So the computational output produced by FHE operations directly cannot be verified. That would require adapting it with zero knowledge proofs, or just running those computations on some ledger, making it even more expensive. And so where we arrive is we need a different kind of technology, and this technology is secure multi-party computation. And that's what we are building with Arcium. And so secure multi-party computation, MPC, allows for a set of participants to jointly compute a function over distributed data that remains private. So the way you can think of it is really as a set of peers, all holding sensitive data, running a collaborative computation. And no one from the set of peers wants or can share their information. Yet they are able to run a computation as if everyone had access to the data. And that's possible through a few cryptographic techniques. One of the main techniques is secret sharing, which is taking those sensitive secrets that each participant holds and splitting them into randomized shares and distributing them. And then only if one has access to all shares, one is able to reconstruct such a secret. And so multi-party computation at the end of the day means taking secrets, sending shares that give no information about the underlying secret to other parties, and then everyone has a set of shares, and they're able to perform local operations and also communication-based operations. And at the end of this entire process, a combination of those shares occurs, which allows to reconstruct the computational output. And with this core concept, we can further extend it with threshold encryption, which means that a set of parties holds keys, and a threshold of those keys can be put together in order to decrypt information. And by combining both concepts together, we're able to build this cryptographic protocol that has some trust assumptions associated. For MPC, there's essentially two major options for what trust one has to have against such a protocol. Honest majority and dishonest majority protocols. Honest majority is something that we see in a lot of blockchain networks with practical Byzantine fault tolerance, requiring more than half of participants to behave honestly. And honesty in this context doesn't mean correctness of computational output, but instead confidentiality of this data that is being encrypted and used in computation. But this trust model is not sufficient enough in our opinion, and so that's why we have the dishonest majority trust model with Archium. That means that for such a set of participants that collaboratively run a computation, there's only one single honest participant required, one participant that doesn't maliciously collaborate with the others. And so that's the kind of protocol that we're building that comes with the lowest possible trust assumption you could have in a distributed system. Any single one honest player is enough. And so the way we implement that is in the Archium network, and we have basically at the moment two MPC protocols at Archium, Cerberus and Manticore. And we have the dishonest majority trust assumption, and under the hood what we utilize is so-called semi-homomorphic encryption. So using semi-homomorphic encryption essentially means we just use a subset of operations from FHE, those that are efficient, and for the very inefficient operations what we do instead is we make use of recent advancements in pre-processing MPC protocols, which split computations in two phases, computation and input independent pre-processing phase and an online phase. By splitting those computation phases, having the pre-processing phase generate so-called correlated randomness, it's possible to bring the execution time of this online phase, where the actual confidential computation with the inputs and algorithm occurs, close to the plaintext speed, very close to the plaintext speed, with minimum computational overhead. And that really allows us to build this very efficient protocol, which comes with the lowest possible trust assumption, the dishonest majority trust assumption. We additionally extended with a few accountability measures, essentially, because those protocols and cryptographic techniques still suffer from a few practical limitations. And that's really the beauty of the system that we've designed, that we take cryptographic protocols that usually would have practical limitations and overcome those practical limitations by combining it with distributed systems and blockchain game theory. And so we, for example, have a protocol that allows to
execute it, defined as like applying it to state. So you change some data.
So we have we extend, for example, our Cerberus protocol for with some cryptographic cheater identification protocol, and then the way that looks like is that with Archium we have a stateless computational network. It's a network that doesn't maintain any single shared state. It just runs confidential computations. And we additionally leverage existing blockchain networks for consensus and state management. We have a permissionless network within Archium, so anyone can run a node, anyone can become an honest player essentially within the Archium network. And the nodes in Archium, all they do is run those multi-party computations, run secure multi-party computations. And for that, they are partitioned into computational clusters. And those computational clusters then get associated with an execution environment. So a user creates an MXE, an MPC execution environment, which is this sort of isolated, encrypted virtual machine instance. And within that environment, they can have encrypted state, and then they can define computations that should happen over that encrypted state. And the corresponding clusters within Archium run the computations for that MXE, and the state can exist on existing blockchain ledgers. So on existing blockchain ledgers, they can have encrypted state, and then it's essentially asynchronous execution of those operations within Archium. And the orchestration happens in a parallelized mempool that exists on the corresponding ledger. And so this is as a contrast to the trusted execution based confidential computation approach, what's possible with Archium. So you see the secret splitting essentially of encrypted data, and then that gets passed to the Archium network. At the end, output is being produced that can be provided to a data receiver. And so with this system in place, what's possible is for anything to be computed. We've designed a compiler that allows any arbitrary program, any arbitrary Rust program or Python programs to be compiled into a format that the Archium network, those MXE instances, can understand and can process securely. It's a purely computational network, and it allows for both confidential on-chain applications and confidential off-chain applications. So confidential on-chain applications, as I mentioned already, can be built by having those environments that exist with encrypted state on other blockchain ledgers, and Archium as the asynchronous processor of the corresponding operations. Confidential off-chain applications, one example would be building confidential machine learning with Archium. And so what we were able to achieve with our multi-core MPC protocol is heavily increased numerical stability by combining different techniques. So having real number arithmetic combined with Boolean arithmetic, garbled and arithmetic circuits, and then performing a new kind of modular lifting and truncation protocol, because the issue in the past really has been representing real number arithmetic and tensor operations within those kind of cryptographic operations. And with our protocol, we were able to overcome those problems by some clever tricks, I guess. Combining all of this together allows us to allow for trustless confidential on-chain applications. At the same time, users can use Archium to run confidential model training, confidential inference on encrypted models. And that's very powerful, and that, I think, perfectly describes the architecture that we are building. It's this architecture that doesn't necessarily care about blockchain. It utilizes blockchain in order to reduce the required trust, make a trustless confidential computing network, but blockchain is just a means to an end for Archium, and developers that are building with Archium don't have to deploy smart contracts. At the end of the day, they just access Archium as this sort of supercomputer instead of working with a blockchain network. And so our vision is for everything to be encrypted and anything to be computed over the encrypted data. Thank you.